So good evening. Can everyone hear me? I think that's the first question. And if so, thank you for coming. Thank you, Geraldine, for that nice introduction. And thank everyone else for coming to talk about volcanoes in our backyard. And we will emphasize in this talk Mount Baker and Glacier Peak, as I believe those are the volcanoes closest to you. As you'll see, this is a talk on behalf of many people in lots of different organizations, because lots of people have worked on these volcanoes actually more than I have. And the knowledge that they've gained is part of what we're talking tonight. So this talk, I'm going to start with a cascade-wide view, just a few slides to sort of set the stage, and then we'll focus in on the general history of Mount Baker and Glacier Peak, what that history tells us about the future of these volcanoes, what we might expect in terms of hazardous processes, and how we translate that information into long-term hazard assessment maps where you can look and find out your relationship to a hazard zone from a volcano near you. We'll then get on to talking about the warning that an eruption might happen, how we learn about that, in essence, how we monitor volcanoes, and then preparing for the next eruption, because that's a big part of what we do. Importantly, I want this talk to answer your questions. So please let me know if something isn't clear or if I haven't touched on a topic of interest. And as Geraldine said, we can discuss that at the end of the presentation, and I'm here for however long you have questions. So let's start off with the fact that Western North America is a geologic hazards wonderland, and that might be a little bit of an odd perspective, but if you're into studying or wondering about big earthquakes, tsunamis associated with them, of course, volcanoes and all the processes associated with those, big landslides, well, you're in the right place for that. So the Cascade Range, which is that mountain range that has all of our major volcanic cones, is the result of the oceanic Juan de Fuca plate being subducted under North America, as shown in this cartoon here. It's a process that has gone on for tens of millions of years and will continue for millions more. So we're into this whole thing of big earthquakes, volcanoes, tsunamis, etc., for the foreseeable future, certainly for all of our foreseeable future. So if you look at this cartoon, as that cold oceanic plate subducts, think about it as if you've got your two fists sort of pressed together, and occasionally, they're pressing together, and then occasionally let one fist slip. And that's what, occurs when we get these big Cascadia subduction earthquakes. We have a large rock breakage over a long area, and that's what gives us our magnitudes 8s and 9s, and it's also the tsunamis that are associated with it. What also happens during subduction, of course, as the cold plate descends, it dewaters, and that dewater helps melt material that's above it. And that material becomes the molten material, or magma, that eventually rises to the surface and erupts out of a vent and creates our volcanoes. The thing about that is that that process also breaks rocks, and so we also get earthquakes associated with volcanoes. But unlike the big Cascadia subduction zone earthquakes, which are 7, 8s, and 9s, what we get at volcanoes are anything from -1, 1.5 earthquakes to maybe up to 3s and 4s, and rarely we might get something that is a magnitude 5. But the earthquakes that are associated with volcanoes is very different from the earthquakes associated with the big Cascadia subduction zone. This map just shows another way of looking at this. It's again the map of Western North America. On the left, you can see the Juan de Fuca plate, where you see all those triangles is where you're getting the subduction. In red is the volcanic centers of the Quaternary of the last 2 million years. You see that it goes all the way up from southern British Columbia to northern California, with the Lassen down here. Let's see if you can see this down here in the Lassen Peak Volcanic Center. So as soon as you cease having subduction, you ceased having volcanoes. So the big earthquakes that occur in the more southern parts of California are not due to subduction, but due to plates sliding next to each other. And that's why we don't see many volcanoes in those areas. So one thing to think about is that volcanoes are a lot like snowflakes. There's a lot similarities between them, but no two are exactly alike. The pictures that you see here, this is a picture of Sherman Crater from Mount Baker, Mount Rainier, Glacier Peak, and Mount St. Helens. And we often talk about sort of analog volcanoes to help us understand sort of the processes that occur, because one analog volcano may have erupted more recently, and we have better information about that, just to help us think about how these volcanoes may react in the future. So if you look at Mount Baker and Mount Rainier, they're two actually very similar. Sorry, I need to do something here because I've got there. They're two very similar volcanoes in terms of composition and eruptive behavior. Both produce lava flows. They don't have any lava domes or associated with them. They have moderate ashfall. Both have experienced sector collapse. And by that, I mean, big landslides off their summits or off their flanks, a la sort of Mount St. Helens, 1980. But even though they're very similar in many respects, Rainier is a more explosive volcano than Mount Baker and has certainly erupted more frequently in the past 10,000 years. If we go, oops, for some reason I'm not advancing there. If we look at Glacier Peak, a good analog volcano for Glacier Peak is Mount St. Helens. Again, they have very similar compositions up in the higher silica range. They are actually lava-producing volcanoes, lava dome-producing volcanoes, which means they often have magma pile up over the vent, making large domes that then collapse and run off the flanks as pyroclastic flows, and then have a big clastic apron around the side of them. They are both very explosive volcanoes, but once again, Mount St. Helens has a wider range in chemical composition, everything from basalt to dacite, and has been more active in the past 4,000 years. So again, many similarities between the two, but many differences as well. In this cartoon, we show eruptions of the Cascade Range during the past 4,000 years. On the left are all in the United States, the major cones from Mount Baker in the north, the Lassen Peak in the south. This is a timeline of 4,000 years. The 200 line is kind of when European explorers first came into the Western United States and started written documentation. And each little icon represents a volcanic eruption. It says nothing about how big that eruption was or what happened during that eruption, but is just a little holder as an event. And as you look at the whole Cascades, what really, I think, leaps out amongst everyone is, Mount St. Helens has been either the bad actor or the good actor, depending on your perspective of the last 4,000 years. If we were to extend this line, however, to the last 10,000 years, this whole period from 4,000 to 10,000 years would be quiet. So some volcanoes are very episodic. When they reawaken, they continue to erupt frequently. And some volcanoes just, do an eruption, then are quiet for a long period of time, and then erupt again. The other thing I should point out in this graphic is that, most of these volcanoes are at least 250,000, most of them 500,000 years old. So this is obviously just a real limited snapshot of their activity. So let's get back to Mount Baker and Glacier Peak, MB and GP in this case. They are both active volcanoes, and by what I mean on that is that they're not showing activity at this moment in terms of eruption, but they're located on an active subduction zone, so magma is still forming beneath them. At Mount Baker in particular, all the traits associated with an active volcano, deep earthquakes, a hydrothermal system, where you get hot waters coming through the volcano, emission of magmatic gases, that all happens at Mount Baker today. Both volcanoes also have young eruptive events within the last couple hundred years. So they will certainly erupt again. The question is, the billion-dollar question, when might that be? And we don't know the answer, but when either does, there's a wide range of possibilities. They could have very minor eruptions, which only affect, the flanks of the volcano, or rather major eruptions with far travel hazardous events that affect the region. And that's one of the big conundrums for us when a volcano reawakens. Most of them have this wide range of activity. And so our job at the time when they reawaken is to look at the monitoring data and try to figure out, is it going to be small, medium, or large? Because that's really going to affect populations nearby. Importantly, neither volcano is currently showing signs of unrest, meaning they're quiet. However, when they do reawaken, we will be able to detect that reawakening with our monitoring networks, and importantly with hopefully visual activity. Hopefully they don't reawaken when we're in a 6-week-long gray and stormy weather. The good part about volcanoes, it usually is weeks to months of warning that they give us. And it's good to know that public officials are already working together to ensure public safety. And this is pretty amazing when you consider the fact that we really don't know whether the volcanoes will erupt from 2 weeks from now, or whether it will be 2,000 or more years from now. But we need to do the work. So let's get a little bit more into what these volcanoes do. So Mount Baker is built by accumulations of lava. That's the molten material that comes and moves downslope by gravity. And fragmental deposits. These are broken up rocks that move downslope under the influence of gravity, hot gas, etc. We call them pyroclastic flows. Of course, it's a volcano that has a lot of glaciers on, and so it's been carved in a way by glaciers, and it's been modified by numerous landslides and volcanic mud flows, or Lahars. If we look at its recent eruptive history, this is the older part of Mount Baker, the Black Buttes, which was active about 250,000 years ago. This poor volcano really got gutted by glaciers, both alpine glaciers and continental glaciers. Built into that gutted volcano is modern Mount Baker, and that was constructed between about 12 and 40,000 years ago, when valley glaciers were generally more extensive than today, and continental ice briefly surrounded the volcano. It's the only volcano in the United States that got surrounded by continental ice. Again, the last summit eruptions were approximately 11,500 to 13,500 years ago. Those occurred at the summit, and then since that time, a new vent has opened off summit, and that's been Sherman Crater, as well as a little vent here in the Schreiber's Meadow area, a little cinder cone. The importance of where the vent is during the next eruption is because areas at risk are related to vent position. If the vent again is at the summit, then all sides of the volcano could be affected. At Sherman Crater, it's mostly the west and south side. And when you have a little cinder cone in a valley, most things don't travel very far. So Baker erupts infrequently. Here's events in the past 15,000 years, and we often focus on those past 15,000 years, this post-glacial time period, because glaciers are incredible erasers, and they erase a lot of the geologic history. So the part of the volcano we know the best is that part of the volcano since the last ice age. We do take in context all of what's happened, but we know that after prior to 15,000 years ago, we're missing a lot of information. So again, between 11.5 and about 13.5, we had lots of summit eruptions with lava flows, pyroclastic flows, and some small ash eruptions, and small volcanic mud flows. Then we had a period of quiescence. We had a little cinder cone that was built in Schreiber's Meadow. A couple of centuries after that, there was some sort of flank vent failure on the side of the western side of Mount Baker. It may have been associated with a little bit of an ash eruption. Then again, thousands of years of quiescence. Our big event at Baker happened 6,700 years ago. It was a sequence of events. First, there were several large collapses on the south and the west side of the volcano that spawned large lahars that moved a good distance off the volcano. Then we had another collapse associated with an eruption that spewed just altered rock, nothing fresh coming up out of the volcano, that was then followed by what we call a magmatic eruption, which is new material coming out of the volcano. And this is the biggest one that we know to have happened at Mount Baker. But again, we're losing a lot of history because of glaciation. And then a very, very long period of quiescence where we see nothing in the geologic record. Doesn't mean very small events might have happened, but they were not preserved till And then until 1843, when again we had a small explosion that was associated with expulsion of altered rock, landslide that spawned a Lahar. And this sort of activity, small explosive activity, may have continued upwards into 1880, but it's a little hard to ferret out the information. It's when European settlers are first coming in, they're making observations, and it's very hard to know how much faith one should put in those observations. And then in 1975, for those of you who were around here at this time, there was a period of increased steam and heat from the volcano for a number of years, but no earthquakes were detected, no deformation was seen, and essentially no eruption ensued. But the thinking is now is that magma got into the upper edifice and just couldn't break all the way to the surface. Glacier Peak, by contrast, is built by accumulation of lava flows, but also by lava domes. And the reason why that's important is that lava domes have this tendency to collapse a lot. So they make up a lot of fragmental material. And so it has a big apron of this fragmental material, which Mount Baker does not have. It also has been carved by glaciers, but not continental ice, and modified by Lahars. It has been more active than Mount Baker in the past 5,000 years, but the big events that really occurred at Glacier Peak happened around 13,000 years ago when very large explosive eruptions happened. These were associated with dome collapses and big lahars that reached all the way into the bay. These events are on the order of maybe 10 times larger than the explosive eruption of Mount St. Helens in 1980. So it gives you an idea of really how big it was. But the interesting part is we don't actually see anything that big since that time period, and we're not sure that it ever was that big before. So it's a little bit of a conundrum why this time period facilitated such large eruptions. And then again, we have a very long quiet period, and then we have a bunch of moderate to small dome growth, dome collapse events up to the present. The last event happened about 200 years ago and emplaced a small tephra deposit. So why is all this history so important? Well, the reason is we kind of consider that the key is, the past is the key to the future of what these volcanoes will do next. Both volcanoes past tell us that the chance of an eruption is low, so it's a low probability event. The fact that it the possibility of it happening during our lifetimes is not high, but the consequences of those eruptions could be large, could affect very large areas. So they're low probability, potentially high consequence events, and therefore we need to pay attention to them. So the past tells us what might happen and what areas might be at risk. On the left here is a cartoon cutout of a volcano, and I'm just going to walk you through, kind of what happens sort of conceptually during an eruption. So magma, for various reasons, decides it wants to head up towards the surface. It's going to start breaking rock. It's going to create earthquakes. Some of the heat might go off into a crack and interact with groundwater and give us, the start of some fumaroles that we might not have seen before. If it reaches the surface with gas in it, early explosions may throw out bombs that could be very lethal to anybody on the upper flanks of the volcano. Again, if it has a lot of gas when it erupts, you're going to get a big eruption column like that big beautiful column we saw with Mount St. Helens in 1980. That ash gets taken down wind with the direction and speed of the wind. And part of it may collapse into a moving pyroclastic flow, which again is a gas rock kind of flow deposits, and we'll see a video of that shortly. Either before or during such an event, you might get landslides happening on the flank of the volcano, but you won't get those, after an eruption is over. If it comes up without a whole lot of gas, what you might get is either a lava flow or a lava dome, which again is just lava that forms over the vent, makes a dome. Those domes could collapse, creating again pyroclastic flows, or they could just be lava flows that come down and the fronts of those might collapse. When you have a hot rock interacting with snow and ice-clad volcanoes like we have, you get volcanic mud flows that go down river valleys and can travel far from source. So we tend to think of these various areas of the volcano in terms of how long it's going to take for hazardous events to happen. And this is important because the emergency managers who have to make the decisions on when to evacuate people or whether to evacuate people need to have some sense of what the timing is. So close-in areas, so summit to kind of the flanks of the volcanoes, can be subject to multiple hazards such as pyroclastic flows, lava domes, lava flows, and these things can reach the base, and lahars, and can reach the base in seconds to tens of minutes. The river drainages that move off the volcano and go down valley, they can be subject to lahars and floods, we'll talk about that, for tens of miles away from the volcano. And, we kind of rule of thumb is it reaches the base of the volcano in less than half an hour, and it, someplace, 20 to 30 miles out may take hours before the lahar reaches the tetrafall, or the big explosive stuff, affects areas close into the volcano, and then tens to hundreds, or even perhaps in big eruptions, thousands of miles downwind. Depending on how fast the wind goes, depends on how long it takes to reach a person or a place, and that can be hours to days, depending how far away you are. And then the last thing that we'll talk about is that with lahars, these volcanic mud flows that go down river valley, the excess sediment that these watersheds get due to either the tetrafall or to the lahar itself can increase the risk of flooding for years to decades afterwards. We call lahars the gift that keeps on giving, because a lahar takes all this material, deposits it downstream in the valleys. It raises the river level, which means there's less freeboard for flooding. And this can continue, like I say, for years to decades afterwards. So Mount Baker's history tells us the main areas of concern are the mountain. Those are for lava flows, flank failures, lahars, and PFs. The river drainages, those that start on the volcano on the east and south sides, are particularly susceptible for both failure and for lahars. And that ashfall isn't very big around Mount Baker, so it'll be mostly a nuisance to communities on ground, and people will not be evacuated due to ashfall, but they may be due to lahar activity. Glacier Peak's history is somewhat different. That the main areas of concern, again, are the mountain. That's true of every single volcano cone here in the Cascades. Drainages on the volcano, the north and the west, are the ones that are most susceptible for lahar activity, and that the ashfall, because it's had these very, very big explosive eruptions, may be a nuisance, just people shelter in place, to very severe, where actually people might have to evacuate because the amount of ashfall that they get. This picture here shows two of my colleagues looking at an ash deposit from Glacier Peak. It's about 30 inches thick, something on similar distance from Mount Baker. The thickest might be something on the order of just a couple of inches. So Glacier Peak just has this much, much more explosive history. We have steep-sided volcanoes, so the lava flow fronts or the lava domes can collapse and travel down slope as fast, hot moving mixtures of ash, rock, and gas. These are the pyroclastic flows we keep talking about. And on the glaciated volcanoes that we have, the hot rock can melt snow and ice to form lahars that then move down valley. This is a short video of a pyroclastic flow from the 1991 eruption of Unzen volcano in Japan. As you'll see, the big cloud is the pyroclastic flow. It's a mixture of rock, ash, hot air. It's very inflated by all the air. The little rectangles you see in the front are buildings that the pyroclastic flow goes over. These are incredibly fast moving, somewhere between 50 and 100 miles per hour. They're very hot, between 600 and 1200 degrees Fahrenheit. They will burn anything in their path. You cannot outrun them, and you cannot outlive them. They're incredibly lethal. Fortunately, they never flow very far off the flanks of a volcano, but it means that you want to be off the volcano when such events do happen. Oops. The next thing we'll talk about other hazards is lahars and debris flows. And so what are these? So these are the volcanic mud flows. There are slurries of mud, boulders, debris, and water that rush down river valleys that head on volcanoes. They too can move pretty fast on steep slopes, but then when they get down into valleys and gentle slopes, they can slow down quite a bit. There's many different types of triggering mechanisms for Lahars, but the largest of these occur during unrest and eruption. The impact is that they destroy all in their path by burial, and they also can just smash into things and cause damage things that way. They fill in river channels with a lot of material. This can increase flooding downstream decades after an event occurs. And of course, you know, the water, it affects the water, so fish, water quality, it destroys bridges, power lines, etc. So anything that crosses a Lahar hazard zone is susceptible to damage. So the guidance we tell people if there's a threat of a Lahar is to obey closure orders and to move off valley floors to higher ground, much like you would do for floods. The left, the upper picture is just a very turbulent Lahar. The lower picture is a very important one. This is the town of Armero in Colombia. You can see, I think, part of the village here and part of the village here. Well, there was a huge village in through here as well. This site is about, there was an eruption of Nevada del Ruiz in 1985. 4 hours later, the Lahar from that eruption, it wasn't a very big eruption, but it was very hot on snow and ice. This Lahar spilled through the village and killed 23,000 people. So it was a terribly horrible event. It really galvanized the volcanologic community worldwide. Make sure this never happens again. The reasons for it was many, you know, combination of poor communication about what might happen, disbelief that a volcano you couldn't see could affect you, the fact that it happened at night, fact that there was a soccer game, so on and so forth. But the sad part is that many people could have survived had they heeded the warnings. So here's an example of an actually relatively small Lahar taken from some French colleagues in Indonesia. And it gives you an idea of the power of, the power of even something that's, you know, really small. So this happened actually after an eruption was over and just had a monsoon come through and remobilize material on the flanks of the volcano. It never bothers me terribly until I see this part. And then I go, oh my gosh, what are they doing standing there? You can see that the Lahar is composed of rock and mud and water. It moves, in this case, quite quickly, still relatively steep. It's basically destroyed this road between it, and you can, I think, understand why people talk about it as a slurry of concrete. Again, they basically bury everything. When you have a big Lahar, if it's very thick, you probably can't expect to re-inhabit the valley floor anytime soon. Also because of the propensity to destroy bridges and roads and stuff, that if you're a community that is on one side of a Lahar zone to another, your community may be isolated for some time. As I've mentioned before, post-Lahar sedimentation can last for decades. Note that we're still dealing with that issue at Mount St. Helens more than 40 years after the eruption. And that post-sedimentation flooding and things can be as destructive as the initial Lahar. A really great example of what that looks like is from eruption of Pinatubo volcano in the Philippines in 1991. This was an area that had been affected early on in the eruption. Basically had taken out a bridge in through here. This is a bridge abutment. scoured the valley at first, and then it started filling in the valley because of all the sediment that was upstream. And here's a picture of the same area, I think a year or so later, and you can see that now the new level is pretty much at the rooftop of this old bridge abutment. So how do we take that information and do anything with it that people then can use to sort of plan for the next event? So what we do is we make long-term hazard assessments that show areas that are potentially at risk based on the past history and likelihood of things happening at the volcano. It does not tell you what areas will be affected by the next eruption, because during any eruption, it's rare that the whole volcano is affected. So this shows all the pathways where either we know that there's been Lahars in the past, where we believe you'll have post-Lahar sedimentation issues, where you might have Lahars or flank failures impact, in this case, the Baker Lake, Upper Baker Lake Reservoir. Should say that at Mount Baker, we've not seen any event in the North Fork of the Nooksack River for the past 15,000 years, but it's not inconceivable that we could get a summit eruption again and affect that area. If we look at the Skagit Valley, the issue from Mount Baker is the fact that if we get Lahars going into Baker Reservoir, and if those dams, the Upper Baker Dam or Lower Baker Dam, were to fail because of that, the worst case scenario would be that we'd end up having flooding all the way into this area. And that, like I say, can only happen if there's dam failure. Reservoirs can be a catchment area. Think about a bathtub that you can fill it up with material, and it just holds the material, so that's really good. Or it can be a problem, and the problem is if you dump a whole lot of sediment into a full bathtub, then you're going to get splash, and that's going to overtop that bathtub. So that's our concern at Mount Baker. In 1975, when there was that thermal event, the Baker Reservoir, Upper Baker Reservoir, was lowered in anticipation of an eruption, and of Lahars entering the reservoir. As it happened, nothing did occur. There was no eruptive event. So it was a precaution. A lot of people were actually pretty pissed off about it. It was a precaution that people took. It just happened in this case that nothing happened. So here's a simplified hazard map, long-term hazard map from Glacier Peak. Again, I guess I should have mentioned this at Mount Baker too, is that this yellow area in through here is this area that could be affected by these near vent processes like pyroclastic flows and lava flows, etc. And this is the area, again, that things can happen very quickly, and you want to have that area evacuated before an eruption occurs. So if we look at Glacier Peak, the pink in here is essentially that same kind of near vent area that needs just to be evacuated as soon as unrest begins. All the drainages that could be affected. In this case, the color scheme is that if you're close into the volcano, you're more at risk than if you're at some distance from the volcano. And that is in a lower hazard. And the same thing as if you're high above the river, you're at less risk than if you're, right down at the risk. So for a place like Cedro Woolley, that's an area that's far enough downstream that it would likely have hours of warning, that once we know that a Lahar has started, that they wouldn't have to evacuate necessarily ahead of time, where a place like Darrington may only get something like 30 minutes warning, so you may have to consider evacuating a place like Darrington even before an event were to occur. The other thing about hazard maps that are important is it also shows you areas that aren't at risk. For instance, if you're in the South Fork of the Stillaguamish River, or out kind of where you guys are, you're really not at risk of anything in particular. This doesn't head up on the volcano, so it's not going to be affected by a Lahar. Your issue is going to be ash, but the wind usually goes from west to east, so it's more likely that areas to the east of the volcanoes will be affected than areas to the west. So speaking of ash, what is it? It's particles of shattered rock that's injected into the air. The bigger particles fall close to the volcano. The finer ones go further and further away. Again, in our area, winds are generally from sort of the west to the east, so the east is more at risk. But of course, if you look at Mount St. Helens in 1980, there were 6 explosive eruptions in the summer of 1980. 4 of them went in that good easterly direction. 1 went to the south and 1 went to the west. So you do have to be prepared for the unusual happening. The fine particles that most people will experience fall at normal air temperature, so there's not an issue there. The impacts are much like the impacts when you're in the middle of a dust storm. You know, the fine particles can irritate the eyes and sinuses, can reduce visibility, as shown in this picture of Yakima midday, where day turned into night because of all of the ash. It's very bad for machines, for electrical equipment, etc. It's not poisonous to either touch or breathe, so there's not that worry. But you know, for people especially who have existing respiratory problems, this can be a real big issue. Most people will be able to just shelter in place, but they may need to get out of there. Again, this is a picture of Yakima, 1980, on May 18th. This is a scanning electron microscope issue. What you can see, it's very pointy, it's glass, it's silica, so it's very abrasive. This is what that fine ash just looks like when you scoop it off the ground. Of course, the guidance during an ashfall is to reduce the nuisance, stay indoors, attempt to keep the ash out of your house, minimize driving and anything that can stir that ash up. As we mentioned early on, Glacier Peak has had some really, really large ash falls. And to give you some perspective about that, hopefully you can see, it's a little grainy, but hopefully you can see this. In the yellow here is the ash from May 18, 1980. And this is showing the ash fall where it is 0.2 of an inch thick. There have been bigger explosive eruption in Mount St. Helens history, as you can see from this kind of line here. That was an event that happened about 4,000 years ago and was between 4 and 6 times bigger than the May 18, 1980 explosive event. Now, if we look at Glacier Peak and that 0.2 inch isopac here, what you'll see is that covers a whole lot more area, and that was at least 10 times larger than the May 18, 1980 event. Of course, we have even larger events occurring in the Western United States. Mount St. Helens 1980 was about 1 cubic kilometer. It's just relative information here. The eruption of Crater Lake or Mount Mazama at 7.6 thousand years ago, or 7,600 years ago, that one was about 50 cubic kilometers, so 50 times the size of 1980 Mount St. Helens. Long Valley at about 750,000 years ago, that event was about 350,000 cubic kilometers. And that covers, in that 0.2 inches, very vast area. But still larger is the Yellowstone eruptions, the last one being about 650,000 years ago, and about 600,000 cubic kilometers, so 600,000 times bigger than the 1980 eruption of Mount St. Helens. But going back to Glacier Peak, again, we had several really big explosions at the end of the last ice age, but have not seen anything since that. And we really, you know, haven't seen anything in that older record either of this kind of big ash falls. But because of glaciation in the area, you know, it's not a great place for preservation. So whether we could have an event like that in the future, it's really, really, really low probability, but we can't rule it out completely. Let's just very quickly, you know, persistent ash eruptions from dome collapse or summit eruptions can really be trying for people. A lot of volcanic eruptions last anywhere on the time frame of months to decades. The last eruption of Mount Hood lasted probably at least 10 years, with probably hundreds, if not thousands, of small dome collapses and ash clouds. This again can affect, you know, your pets, your livestock. We used to tell people that they should shovel ash off their roofs. Most of the Cascade volcanoes don't produce enough ash to make that very meaningful. We learned that up in Alaska when people were shoveling ash off roofs, and more people were falling off the roofs than there was ever any danger of the roofs collapsing. So we no longer advise people to do that. You know, it really is bad for mechanical instruments like cars, airplanes, etc. So the other issue about ash is it can really hamper rescue. So, during an ashfall, people have to be pretty self-sufficient. So how will we know when Mount Baker Glacier Peak is getting ready to erupt again? Well, volcanic eruptions are pretty neat because they're unique in terms of natural hazards. This little graph shows, some of your normal natural hazards, the event, how much warning you might get for that event, and the duration of those events. So, floods often, the Weather Service can tell us, maybe a week or so in advance that, the conditions are right for flooding. Usually the floods last for a couple of days and they're over. Hurricanes, much the same thing. The warning might be actually weeks, but really getting real a couple of days beforehand. And again, the hurricane itself usually passes through in a matter of days. Earthquakes and tsunamis are more or less instantaneous. They happen, and then the after effects or aftershocks might last up to weeks or months. Wildfires, same kind of thing. We may know that the event is it's very dry out and it could happen, but usually until it happens, so it goes. But with volcanoes, we can actually have months to even years of unrest at a volcano before the actual new material reaches the surface. That's what I'm calling the event. And then again, that event can last then for anywhere from months, days, weeks, months to decades. The longest volcanic eruptions have gone on for almost a century. So the good part is volcanoes do give us warning signs. And again, they usually show that weeks to months in advance. So what we're looking for is increased earthquake activity, increased gases, and changes in the ground surface. This little cartoon will just walk through what happens. A magma, which is 3 to 5 miles beneath our feet, summit of a volcano, decides it wants to start heading up towards the surface. As it heads up, it has to break rocks. We hear those rocks as that breakage as earthquakes, and we measure it as earthquakes. As it goes from high pressure to low pressure, it releases volcanic gases, and there are different types of species that get released. So we get some idea as to how close the magma is to the surface. And depending on, as the magma leaves, an area, it may contract. So things might get closer together on surface, or it might deform by stuff up here closer to the surface starting to expand. Earthquake monitoring is really our kind of primary monitoring tool. We have lots of them, but it's a 24/7 monitoring tool. You stick the seismometer in the ground, it gets relayed to the observatory, and so we have a constant record of what's going on at volcanoes. You can see this, our partner with this is the Pacific Northwest Seismic Network out of UW. They have a wonderful webpage that you can go to. Just go to PNSN, go to the volcano webpage, and you can see any earthquakes that are happening at these volcanoes. And so you can monitor them along with us. And it will give you information as to the size of the earthquake, the depths of those earthquakes, when those earthquakes happened, etc. You can also sign up for, via the USGS, a volcano notification service, which will actually ping you when an earthquake of a certain size at a volcano occurs, or you can follow things on Facebook or now Instagram. So depending on how geeky you want to be about this, you can get a whole lot of information about the volcanoes and, like I say, monitor them with us. But in addition to the earthquakes, we really have a lot of tools in our toolbox, and those keep expanding almost with every year to look for monitoring volcanic activity. Really, the big thing that has been of the last decade has been remote sensing. We see gases from space now. We can see hotspots on volcano from space. We monitored lightning around volcanoes because that tells us when the ash is in the atmosphere. We have our seismicity. We can do ground deformation. We have multi-gas sensors now that we place out at the volcano. We detect lahars or volcanic mud flows. So really, it's using as many tools as we can to detect unrest and eruption once unrest occurs. But really one of the best monitoring tools is still our eyes and our brains. So when we can see volcanoes, that's really good. The USGS, we're the ones who are responsible for giving you alerts. That's our mandated responsibility. We have a volcano alert level notification system that's good for all the volcanoes in the United States. These are alert levels based on the behavior of the volcano, not as to the risk to populations. We have one for people on the ground and also one for people in the air. I've not talked much about aviation, but ash is really deadly for planes if they fly through it. The reason being that the ash, which is just a bunch of glass particles, melts at the temperature basically of your jet engine. And so if you ingest a whole lot of ash, you melt it, you coat the engine, and you can cause engine failure. So we in particular want to keep planes away from ash, and our desire is to be able to give the aviation industry warning within 5 minutes after a volcanic eruption begins. So how are the officials and scientists responding to these potential hazards? So for all the volcanoes in Washington, we have a hazard work group. And in the case of Mount Baker and Glacier Peak, that's been sort of combined together as the Mount Baker Glacier Peak Hazard Work Group. It consists of scientists from the USGS and from other agencies. It consists of emergency managers at the federal, state, local, and tribal. We've put together interagency response plans, how we're going to communicate with each other, who's going to do what role, who has what roles. We periodically exercise that plan. We do some community outreach, but we have lots of information on both emergency management and also on USGS website. And we do have educative materials available for anybody out there who might be a teacher. Something I wanted to say, I wanted to say something here in the community outreach. You know, it's really great to be able to talk to you folks tonight, but you know, what we mostly do focus on, to be honest, is with the emergency, the first responders, and with the media. And the reason being is that we're about 70 people, you know, we added another 70 with academics and other people who work on volcanoes, but it's a relatively small group for the population at large. So our focus has been to make sure that those folks who actually have to make the hard decisions, like the emergency managers, are as well informed as possible. And then also the media we work with quite a bit, because they are really our, they're the ones who talk to all the rest of the community. So that's kind of where our focus has been. So during this whole thing, there is, in my mind, we have a science role for people like me. And our role is to decipher the eruptive history of these volcanoes, to delineate those hazards, to give warning through our monitoring. And here, I got ahead of myself, communicating and working with public officials and the media. And again, the reason being is just the small number of people working on these volcanoes in relation to the population at whole. And that population at whole is a very transient population in many cases. So it's, you know, it's a lot to keep up with everybody. But the main point here is that a successful crisis response requires that we monitor volcanoes, that we do as much science as possible, and we do as much outreach as possible. And you can look at volcanic, what do I want to say, disasters, I guess, around the globe, both here in the US with Mount St. Helens, 1980, the example I gave you of Colombia with Nevada del Ruiz, and so many others. And whenever there is a case where a large number of people have been killed, it's usually because there's been a failure in one of these three arenas. And so it's really important that we actually do all of them. But the public has a role too. And your role is to learn about volcanic issues in your community, just as you are tonight. And look at these hazard maps and decide whether you live, work, go to school in, or frequently cross one of these hazard zones. And if so, you know, what are you going to do about that if that volcano wakes up? So you need to have a plan for how you and your family respond to the event of a volcano. And this is really not much different from, you know, any planning you do for natural disasters. So we don't want to leave you with the impression that, you know, volcanoes are somehow you got to do something extra or something special about volcanoes. It's just that for all of these natural hazards, it's really important that you have a plan of how you're going to address that with your family. And of course, stay informed. And again, as you are doing tonight. And this is especially true if, in this case, either the volcanoes show signs of unrest. Obviously, then you really want to listen to the media and take public official warnings quite seriously. Where you're living, again, the hazard from these volcanoes is relatively mild. You're mostly going to be wondering or worrying about whether or not there'll be an unusual wind pattern the day that a volcano erupts. But the good part is if you hear the volcano erupts, check out the wind and you'll know whether you're going to get ash or not. And you could probably even calculate about when you might get that. Another thing that we actually, would request of you is to call us. And I give you our phone number here on the screen. If you see or feel anything unusual at the volcano, we're down here in Vancouver, Washington. You guys are up there closer to the volcanoes. You're probably spending more time on the volcanoes than we are. So we actually really do rely on a lot of people's impressions as to whether things look normal or don't. What happened in 1975 was really the general populace seeing that there were dark clouds over, Mount Baker. And it wasn't any monitoring. At that time, there wasn't any monitoring instruments on the volcano. There were a bunch that got on very quickly thereafter through the University of Washington. But again, it was really the public who saw this unusual activity and warned the scientific community about it. What we're really looking for is persistent unusual events versus one-time kind of events, or versus sort of common events. And by common events, I think for most of you who have spent time looking at Mount Baker, you realize that in the wintertime, when it's very cold and it's windless, you actually see the vapor plume being emitted from Sherman Crater. That's happening all the time, but the only time you're going to see it is really when it's cold and that vapor plume is condensing. So the last thing, of course, is, cherish your backyard volcano for all of its wonderful aspects, and there are so many. It's water, wildlife, skiing, hiking, just aesthetic beauty. They give us so much more, and just every now and then tell us we should stay a little away. So with that, thank you for your attention. I really appreciate it, and I'm open to take any questions. I realize I really have covered a lot in a short amount of time, so please ask away. Thank you.
All right, thank you so much. Let's see, we have a few questions here. What is the difference between an alpine and continental glacier?
Okay, good question. Sorry that I didn't make that clearer. So the alpine glaciers are the glaciers that are on the volcano, and the source is the volcano. So you look at Mount Baker, Glacier Peak right now, you'll see a lot of snow and ice on the volcano, and that's because they're very tall peaks. A lot of snow accumulates, and that gets turned into ice and moves and becomes a glacier. The continental glacier is during the last ice age, when there were, huge, broad sheets of ice that were coming out of the highlands of Canada that were flowing down into the upper parts of the United States. Those were the continental glaciers. They're, large in scope. They don't start at the volcanoes. Their source is elsewhere, and they move. And they were very, thick in the Puget Sound lowland. They were, upwards to 1,000 meters, 3,000 feet thick. Alpine glaciers that start on the volcano, might get up to thicknesses of several hundred meters, kind of thing. Hopefully that answers that question.
Yeah, thank you. We've got another one here. What is a negative magnitude earthquake?
Okay, so the Richter scale was the first and original, excuse me for a second, was the first system that we had that put the size of earthquakes into a relative scaling. And the thing is that was a system that was developed back in the 1930s, I believe. And so the sensitivity of instruments were not as great as they are today. And so as the sensitivity of instruments have increased, we've actually can detect smaller and smaller earthquakes. And so those have become into that negative earthquake magnitudes. And so it just reflects the fact that the original schema and system didn't have as sensitive instruments as we have today. Because we have more sensitive instruments, we can detect things that were smaller. Instead of redefining the whole scale, we just put things into a negative, which indicates very, very tiny, very, very small volumes of rock breakage.
We have another one. A UW professor said that, I'm not sure how you pronounce this, Blowers Bluff or Blowers Bluff, which is in the north end of Penn Cove on Whidbey Island, that it's a Lahar from Glacier Peak eruption. Do you know anything about that?
On Whidbey Island, I'm afraid I don't, but I can ask somebody else about that and get back to you. So if Geraldine, if you can send me that question directly through an email, I promise to look that up and get back to you to send that to whoever asked the question.
All right, yeah, thank you. I will do that. Let's see. I once saw at OMSI that Oregon was created in recent history by volcanoes from the east. Is that true of Washington?
I'm sorry, start the beginning of that question again.
Sure. This person said, I once saw at OMSI that Oregon
Oh,
was
OMSI, okay, thank you.
That Oregon was created in recent history by volcanoes from the east. Is that true of Washington?
I'm not exactly sure I totally understand the question. We have had volcanism in Western North America for quite some time. The Cascade Range is relatively young, 2 million and younger. There is older rocks on both the east and the west side of the Cascades from earlier volcanism. The other thing that has happened with in our area is we have accreted terrain. So we have, material that has come from elsewhere that has moved with plates and crashed onto the margin of North America. So we have a really complex history, both of that volcanism and of this accreted terrain. In addition, we've had the hotspot that has North America has gone over, that has created a lot of volcanism. You see this a lot in Oregon. That created, the Yellowstone hotspot. But as that North America was migrating over that area, you got volcanism associated with that as well. And the volcanism actually gets younger as you go from east to west. So that might be part of what people are seeing, but it's a very dynamic area with lots of different things happening.
Is there activity going on even on a small scale today at Glacier Peak?
At Glacier Peak, we don't have a lot of instruments there. We only have one seismometer that's on the volcano itself, and then we have just a couple that are sort of regional seismometers. And it's a pretty quiet volcano, unlike Mount Baker, where we actually see these deep earthquakes, where we have magmatic gases coming out, where we have fumaroles in Sherman Crater. We don't see that kind of activity at Glacier Peak. And that might be in part the lack of monitoring equipment, at least for the earthquakes, but probably not. Probably those things just aren't occurring at this time. And, they both have had eruptions within the last couple hundred years. Why we still see vestiges of that at Mount Baker, but we don't see vestiges of that at Glacier Peak is really not known. The other volcanoes that have had recent eruptions, like Mount Hood, which erupted in the 1780s to early 1790s, and Lassen Peak, of course, which had eruption in 1915, 1917. You know, it's interesting that all these three volcanoes, Baker, Hood, and Lassen Peak, we see fumaroles, we see gas, we see earthquakes. But some of these other volcanoes that have shown, you know, recent activity, they just seem to be quiet right now. And what the difference is between the two, between these systems, one showing these vestiges and others not, we don't know. I mean, Mount St. Helens, interestingly enough, even for its, I mean, it is still always the most active volcano in terms of earthquakes, but it doesn't show as much in terms of magmatic gas coming out of the volcano. And again, you know, some of these differences, we're still trying to puzzle through what that means.
Is the lack of monitoring on Glacier Peak, is that mostly due to the remote nature of the volcano, that it's hard to get to, or are there other factors?
Well, that's certainly a big part of it, is the remoteness. It's you know, all of these volcanoes are currently in wilderness areas, and to respect wilderness, there's, you know, you're allowed to do a certain amount of scientific activity there, but it's also curtailed to a certain extent, because they don't, you know, part of wilderness is not to have mechanized equipment in those areas. And so, you know, it's a conversation between the land managers and, you know, the scientific community in terms of getting instruments in. It's a question of money. It takes a lot of money for, you know, having these campaigns and monitoring these volcanoes. So we have to sort of always parse through, you know, what do you think is most likely to happen? Where is the most dangerous kind of activity? So what volcanoes do you need to have really well monitored to perhaps not as well monitored? The long-term plan, of course, is to bring monitoring up throughout the Cascades to a higher level than it is today. There's a plan that was back in 2005, there was a report called the National Volcano Early Warning System that was published that ranked volcanoes within the United States in terms of being high to low hazard. Certainly all the Cascade were either very high threat or high threat volcanoes, simply because of their proximity to populations. Glacier Peak, you know, Darrington's there. The Sauk-Suiattle tribal lands are in Lahar hazard zones, so obviously there's a big concern, but you know, the population density around that isn't as great as, say, a volcano like Mount Hood. So it's a number of factors. It's a long-winded answer, but it's because there are a number of factors, and, you know, getting to Glacier Peak and getting instruments on there is, it's tough, and it takes a lot of money, and it takes the willingness of the land manager to also let us do some of that work. And that varies from place to place.
All right, it's not a volcano, but do you know anything about Mount Pilchuck?
I'm afraid I'm showing my ignorance by saying, no, I don't.
Okay. Regarding the chart showing eruptions over the last thousands of years, aside from examining sediment and carbon dating, can you explain how we know when these occurred?
So our primary way of knowing these recent eruptions is, as the person indicated, is through radiocarbon dating. The other technique that we often use for relative dating, not absolute dating, is paleomagnetics. And so as hot rock comes out and cools, it locks in the direction of the Earth's magnetic field. And we can date certain rocks, know what that Earth's magnetic field was at that time, and then we can use that information, combine that information to date to look at other rocks that we think may have erupted at similar times, where we might not be able to find any organic material in which to date it. So the organic material is incredibly important for us to find. That's how we get the absolute dates. Argon dating mechanisms actually really don't do very well at, you know, in the last couple thousand years. We sometimes can use thermolescence dating of sediments. We can sometimes use, you know, the relative actually glaciers. The glacial history helps us to be able to date some kinds of events. In fact, at Mount Baker, knowing the glacial history has been really important in being able to figure out kind of times when the volcano has been active and the volcano hasn't been active, because there have been these big glacial lakes around the volcanoes from the retreat of the ice, the continental ice, that has given us data and information that we wouldn't have otherwise. So again, the absolute age mostly comes from carbon age dating. Then there's a lot of relative age dating techniques by looking at the relationship between volcanic deposits and glacial deposits, looking at the magnetic signature of hot rocks. And those are probably our primary ways of figuring things out. We don't have a very good record, and I don't know if it's because there isn't a very good record or that's been preserved, or, you know, whether we just don't have the right communication with Native Americans in terms of volcanic eruptions in the Cascades. There's an interesting, you know, there are other natural phenomenon that there's been great Native American oral histories that have helped, you know, decipher the volcanic history. In particular, over in Hawaii, there's a very rich oral Hawaiian history that really tells a lot about what's going on with volcanoes. We don't know of that so well here in Western North America, and it may be that we just really need to sit down and get to know the Native American community better than we have. And that's something that we are planning to do, want to do, but really haven't gotten very far. And that too may actually help us with understanding this most recent history at these volcanoes.
All right, it looks like we've got one more here. When these lahars stop flowing, is there a relatively consistent pattern of recovery or recolonization of species, for example, plants, many animals, or fungi, due to debris and nutrients in the lahars, such as the 1980 Mount St. Helens eruption, or is it variable and episodic and relatively unpredictable?
I'm thinking about that. It's a very intriguing question. So the Lahars, so at Mount St. Helens, going back to 1980, you know, you had a series of events. It started with the big collapse, then the lateral blast, and then you had the, you know, vertical eruption column that produced Lahars kind of early in on the morning of May 18th. And then in the afternoon of May 18th, that debris avalanche, which had a lot of ice and water in it, there became a pattern, you know, or a coalescing pattern of water that then flowed off kind of the debris avalanche and made the big North Fork Toutle River Lahar. So in that particular case, you know, what we see in terms of the recolonization and the succession of plants has been not so much on the Lahar, but on the debris avalanche deposits, so the big landslide deposits. The river drainages, such as the North Fork and South Fork of the Toutle, those, you know, are still pretty active. And so in the channels themselves, what you've gone is from a river that was, you know, kind of a single channel river to a very much a braided channel river. I'm thinking on these other flanks of Mount St. Helens, and I'm coming back to Mount St. Helens because it's such a great example of, you know, a place where we've actually gotten to observe these kinds of events in the Cascades. You know, on the other places where the Lahars weren't very big, they've sort of recolonized more or less the same way as the debris avalanche is recolonized. You're starting to get a whole lot of different species coming in, and starting with the lupines and lupin and other plants. I mean, one of the very cool things that they learned from Mount St. Helens is which I think in some ways we intuitively know, but we didn't really know in another way, is the fact that it isn't, one plant, then another plant, then another plant, that you actually need the symbiosis of multiple species and multiple insects and multiple small burrowing animals sort of all at once to repopulate an area, and that it doesn't just go sort of monotonically from one to another. Again, I'm not sure if I'm sort of really answering the person's question, but those are my musings about it, I guess, nonetheless. So it's hard to say that every place, repopulates in exactly the same pattern. Every event is somewhat different, but especially in river systems, which can be so dynamic, it just takes a while for, the river to go from, if it was a single channel, it takes a while from it to get back to a single channel. It mostly will go from single channel to a braided channel and then back to a single through time. But it will vary from place to place as to how long that will take. And it depends a lot on, in the area, whether it's steep terrain, gentle terrain, a lot of storms going through, affected a lot by snow melt and so on and so forth. So every place will be somewhat different.
All right, well, thank you so much for taking the time to talk for us this evening and taking extra time to answer questions. I really appreciate getting to hear about some of the volcanoes that we don't get to hear about as often, especially since they're so close to us. And thanks everybody for joining. Someone asked where they can see the recording. So for those who joined late or want to share with a friend, it will be on our WSU Extension Island County YouTube channel. I'm hoping to get that up sometime tomorrow. So there's a lot of thank yous in the chat I'm seeing as well. So,
well, I thank all of you, and it's well, I wish I could see you, but I really appreciate your interest, and thank you for sitting through it all.
All right, thanks again, everybody. We're going to take the holidays off from the series and look out for us again early in the new year. All right, have a good evening.
All right, thank you.
Yeah, thank you.